Okay, so in this problem we have a cyclist. They start from rest and accelerate uniformly at a rate of 2.5 meters per second squared for 8 seconds along a straight path. Afterward, they maintain a constant velocity for an additional 12 seconds. We want to figure out... So let's start by, instead of drawing like a cartoony picture, I'm actually going to consider what's happening to their velocity as this is happening. So if I think about this is time, this is velocity, they're going to start from rest, right? And they're going to accelerate uniformly. So that's going to be increasing at a constant rate because the slope of this line is the acceleration. And after 2.5 seconds, 8 seconds, they're going to hit a constant velocity and move forward for an additional 12 seconds. That would be a total of 20 seconds. So let's write down all the information that we have here. I'm actually gonna break this into two different types of motion. I'm going to call this A and this B. So for A, my initial velocity is 0. I don't know what my final velocity is. I have an acceleration of 2.5 meters per second squared, and I know that this lasts for 8 seconds. For part B, I have no idea what the initial or final velocities are, but I know that they're going to be equal to each other. I know that my acceleration is 0 because if we maintain a constant velocity, we can't have any acceleration. Right? Acceleration results in a change of velocity. So if we have a constant velocity, we have no acceleration. And we know that this time is going to be 12 seconds. I can also add some additional information. I know that my initial position is going to be 0 because I'm just going to make the initial position 0. And I know that they're going to be moving forward in the positive x direction this entire time. So this is going to be a kinematics problem. And I'm going to go ahead and write down my kinematic equations. Okay, now that I have my kinematic equations written down, I am going to try to solve part 1. So part 1 asks us, how far does the cyclist travel during the first 8 seconds of the acceleration? So it's asking us to find this change in position. Well, I know that my initial position is 0, and a change in position is going to be final minus initial. What I'm really looking for is this final position. So let's figure out which kinematic equation we can use here. We want to find an equation that involves either a change in position or the final position. So automatically, I know that I can't use equation 2 because this doesn't involve position. Now I need to consider what information I do not have. I don't have any information right now about what the final velocity is, meaning that equation 1 can't be used because we have that average velocity, and equation 4 can't be used because that requires a final velocity. This means that the only equation I can use is equation number 3. So equation number 3 is the final position is equal to the initial position plus the initial velocity times time plus 1/2 at squared. Thankfully, I don't have to do any rearranging because my variable that I'm solving for is already by itself on the left-hand side, so I can just start plugging in numbers. My initial position is 0, because if I think about like a number line, I start here, I'm going to be moving forward. I can consider this to be x is equal to 0, and then we will be moving forward to x is equal to some location, right? So My initial position is 0. My initial velocity is 0 times time. That's not going to matter. That'll cancel out. Plus 1/2 times my acceleration, which was 2.5, times time, which was 8 seconds squared. And we are going to get that our final position is going to be 80 meters. So during that entire first 8 seconds, the cyclist travels 80 meters. So 80 meters. Then it asks us, what is the cyclist's velocity at the end of this acceleration? So I'm going to go back to my formula sheet here, and right away my eyes were drawn to equation 4 because I have that delta x, I have acceleration, it's asking us for the final velocity, so I'm just going to go ahead and use equation 4, which is our final velocity squared is equal to the initial velocity squared plus 2a delta x. Remember that when you take the square root of something, you have to do plus or minus the square root because either option is valid mathematically. We have to use our physics intuition to determine if it's going to be positive or if it's going to be negative. So I'm going to go ahead and plug in all these numbers. My initial velocity was 0 plus 2 times my acceleration was 2.5 times 80 meters, and I get that my final velocity is going to be plus or minus 20 meters per second. I know that this has to be positive because it started at 0, it moved to 80 meters, right? It moved in the positive direction. So our final velocity for the acceleration phase is 20 meters per second. The next thing it asks us is to determine how far the cyclist travels during the constant velocity phase. So for part 3, we want to figure out what is the change in position whenever our acceleration is equal to 0. So now we need to figure out which one of these equations we can use. Well, I need to pick an equation that has delta x. If I pick equation 4, this will not work mathematically. My acceleration is equal to 0. That would cancel everything out. That would get rid of my x. I can't use this equation. I could use equation 3, right? Because I'm solving for a change in position. If I move that x initial over to the other side, I would get final minus initial, which is delta x. That's what I'm solving for. I have my initial velocity because my initial velocity is this final velocity at the end of the acceleration phase, right? Because this has to be a smooth transition from acceleration into constant motion, if I figure out what my final velocity is at the end of the acceleration, that's going to be the velocity for the rest of the motion of the cyclist. So, I have time, and my acceleration would cancel out. I'm going to pick equation 3 again. I'm going to be honest, you guys. Oftentimes, equation 3 works for almost any problem. It may not be the easiest one. Sometimes it will shove you into the quadratic equation, but almost every single time you're able to use an equation like this. I think I use this equation more than I use any of the other ones. So I'm going to go ahead and rearrange this to get delta x. So if I move x initial over, I get final minus initial is equal to initial velocity times time plus 1/2 at squared. This is delta x is equal to initial velocity times time plus 1/2 acceleration time squared. Now I can start to plug in information. So I have delta x. My initial velocity was 20 meters per second. I know that this is going to last for 12 seconds, and because my acceleration is 0, that cancels out. This means that the total change in position of this cyclist is going to be 240 meters. This person is not on a bicycle. Like, let's just leave it at that. They're on a motorcycle or something. This is not bicycle. I can't bike this fast. So the change in position is 240 meters. keep in mind, this is just the change in position on the axis, right? So if this is the moment where our acceleration is equal to 0, this is the first, how far did he go? 80 meters. This is another 240. His final position would be 80 plus 240. So the final position would be 320 meters. This is just his change in position. I don't know why I'm saying his. I guess I'm assuming that this cyclist is a man. That's something we should talk about. What is the total distance traveled by the cyclist? Oh, I already solved that. 320 meters. It's the total distance traveled by the cyclist.